Hello, everyone. Good afternoon. Welcome to this talk on the data science section. Today we have with us Bertha Amelia. Bertha Amelia is an operations engineer with National Oil Well Baku. She currently resides in Stavanger, Norway. Bertha has an educational background in applied geology. When Bertha doesn't work offshore on the oil rigs, she spends most of her time running analysis of clients' wells data, mostly using pandas and Scikit-learn to help extract quantitative information that can aid the clients to make important operational decisions. It's my pleasure to welcome you, Bertha, and we hope to benefit from your talk today. And to our viewers who are following this live stream, you can drop your questions in the comment section to Bertha, who will take her time at the end of the presentation to answer your questions. Okay, Bertha, the floor is yours.
Okay. Hi, everyone. Thank you, Idris, for the introduction, and thank you so much for giving me a time slot to present this topic. So let's start. Like Idris has said before, I work in the field. I work as field engineer, so I'm not a data analyst by profession. So for me, I'm still learning, and that's why in this session I would like to have more open discussion, and I really welcome any feedback or input to improve the current method that I'm doing. So let's start. So the topic today, it will be about building a classifier model to determine borehole stability in oil and gas well. So the borehole stability in this topic is related to the tight spot prediction in the well bore. And so why do we want to build a classification model? What is the significant value of having a model? The ultimate objective to build this model is to predict to have prediction of where the tight zones are, especially in exploration well, where there is very minimum data available, and therefore there are greater risks when drilling the exploration well. So to have this prediction of where the tight spots are, it really reduce the risk of having borehole stability issue. For example, pack off that is so common in exploration well, or well bore collapse, or swap or search during tripping in and tripping out. So if the well operators able to have this prediction ahead before they design drilling program, then it will give enormous value in minimizing lost time. And then second is the drilling optimization. This is pretty much the subsequent result of having a good grip of well control. For example, here, can I increase my rate of penetration? Can I increase my RPM? Will it be safe enough? And what will be my label looks like? Is it going to be tight spot or not? Is it safe or not if I increase the ROP? So again, with that, if the well operators able to have these predictions ahead of drilling, then they can maximize the drilling optimization parameters to get as safe as possible. And then the third one is to leverage the data. So by using the open source in Scikit, then it's kind of give considerable leverage to the users or the data owners themselves to be actively contributing and adding values to the data that they already have. And lastly, the requirement for creating this classification model is that the borehole size of the testing dataset, the borehole size of the training dataset, it must be similar as your testing dataset. So for example, if you use 26-inch borehole size as your training dataset, then it is only applicable to test another well of 26-inch borehole size as your testing dataset. Otherwise, then your model will not be very accurate, because this is due to the differences in the well profile for each section. Different section has different fluid dynamics, so you cannot assume those parameters you have in one section is going to be exactly the same to another section. So that is the benefits of having this model. And then next we go to the problem description. So here, for example, when you drill, when you have exploration wells campaign, you normally drill a batch of wells that are close to each other. So, for example, in the diagram, we have well A, and then we have well B and well C. When you first drill well number one, which is well A, and then you acquired all these drilling parameters. And here I chose five parameters: hole depth, weight on bit, bending angle, downhole torque, and ECD as features. And my label will be just discrete values, 0 to 1. So 0 as normal zone and 1 as suspected tight zone. So the question here is, if I'm able to build a classification model using well A as my training dataset, can I predict the tight spot in well B using the same features? And also the same, can I predict the tight spot in well C? Is if they are drilled at the same platform, is it going to be relevant? So that's what we're going to answer today. Okay, and then so moving to the number one step, which is pre-processing. So pre-processing is a big chunk of work in the beginning. So I suggest you to take your time and consult people of what features that you would like to use. For classifier, it's always best to have features that are contrast to one another. So, for example, here, if you see in diagonal in the diagonal diagram, the hole depth and the weight on bit. So the tight spot is in orange color, and the normal region are just in blue shades. For example, in the hole depth, you can see tight spots are normally observed in the deeper counterpart. And then it has also a slightly higher weight on bit and a slightly lower torque compared to normal, and also lower, like very low bending angles. And lastly is tight spot here has very high ECD values compared to normal zone. So this is the ECD here, I would say the number one predictor, because they are very distinct to each other. Where you find tight spot, normally it's closely related to high, extreme high ECD. ECD in this case is the equivalent circulating density. It's the measure of the density downhole when it is continuously pumping. There is continuous flow of mud. So, okay. So, I don't know. Oops, sorry.
It seemed that we lost your presentation.
Right. Can you see it now? Hello? Oh, okay.
Yes, everything is okay. You can continue now.
Okay. Right. Sorry about that. Right. Yeah, I'm gonna continue now. So, right. So, yeah. So, out of 5 features, then I choose two as my main features, which is torque and my ECD values. So in here. And the number one, after we chose our features, then we want to clean the data. When you generate the last file, normally you have a lot of missing data. So make sure you remove all those missing data and you clean it using imputation method. There are various way of how to fill your data, and in this case I'm using mean strategy to replace my missing data. So it's really case to case basis. You can use either mean, or you can use median, or the most frequent data set. And then so then we go to the algorithm itself. I first tried the SVM algorithm here, and the way SVM works is that it creates a hyperplane, as you all see here. So it creates a hyperplane, and then from there on, it's gonna establish margin along its support vectors. And so this margin acts as a constraint. So any data set, any data point that fall outside the margin, then it's gonna classify that data point according to the nearest class. So In the real data set, here I've plotted the torque and ECD and also the support factors. I drew it from Python, and then yeah, so it's not as clean as the ideal one. In here, the margin is quite narrow. I set my C as 100, so I just want to like draw a hard margin, but it seems pretty okay here. Seems like the support factors are not that bad, but this is what we're going to test if our predicted values are actually reliable or not, right? So uh, just to have a quick glimpse of my data looks like. So I'm just trying to run like a regression instead of the classification. Here, I'm not sure if it's recommended or not, but I still try it. This is just, yeah, I just want to know if my kernel that I'm using is good or not. So I knew my label is just going to be 0 or 1, 0 as normal and 1 as tight zone. So anything that is negative, I would just assume that that model is not correct. So in here, my for example, when I use a linear kernel, I've got like minus 0.0, but it's still close to 0. And then when I use the RBF kernel, then it gives somewhat close to my actual. So it's just to have a basic idea of how my prediction will look like. But in general, I believe the default kernel RBF is meant for polynomial, while the data that I have here is more linear. So I would go with the linear instead. And here is the result. I'm using here the well A as my training dataset and also testing. So it's just it's still in one dataset, which is well A. And I see here the my accuracy is 0.99, which is very high, and my C is 10, and another one I see my C is 5, and also with RBF. So I would not I can't really trust this accuracy that much. So I need like another method to evaluate my model. But we can compare first with another kernel, which is linear. And here also I got accuracy just as high. It's like almost, yeah, it's perfect accuracy. It's 1. And it's probably 0.999 something, but it's rounded up to 1. And seems to me linear is not that bad. So here, after I train my model with well A, and then I try to implement the dataset of well B and see if my predicted values are close to my actual values or not. And here is the result. So for accuracy, I got 0.99 for RDF and 0.97 also with linear. And even though it has high accuracy, but I doubt that it's reliable, because as we see here from the confusion matrix, if you see the confusion matrix here, the true positive is what we want to see, right? So all the basically in confusion matrix, you want the non-diagonal value, which is false positive and false negative, to be like as close to 0 as possible. And here we have true positive of 155. So out of 8 and 2, out of 528 observed positive, it's only 155 that is true. So that is not so good of a prediction, I would say, like, because more than half of it are wrong. And now we switch to C equals to 100, uh, which is a much narrower margin. And with this, I could see that my confusion matrix produce much more reliable, much more reasonable results. So I got 496 true positive values out of 528. So it's quite good results. It's close to the actual values, and good high accuracy as well. So I would go with these parameters if I want to test another data set, for example, in well C. So that's all. And here is the second best approach for this type of problem is the KNN algorithm. Both KNN and SVM are good techniques for categorical classification models. The difference is just while SVM has already a boundary that can distinguish different classes, in KNN it doesn't have that assumption. So in a way, KNN is there is only k parameter that you need to assign, and depending on how many k, it's just gonna go around its neighbor and then classify the new data point depending on the majority of the neighbors. So for example, here you have k equals to 3, and the data point, the black color dot here, is going to be classified as red because it has a majority than the blue color. So the challenge is what value of k will you use for this type of data? You don't want it to be overfitting. So in this case, when I'm experimenting with the data, it's good to have different k plotted. So in this case, I plot k against the mean squared error. I got the k equals to 3. It has the lowest error, so I would go with it. And also it has quite high accuracy. And one way, because the problem with tight zones is that it's normally clustered in a very particular depth interval. So when you do training and testing in one data set, it's kind of increase the risk that your testing does not represent the whole distribution of your tight zone. So one way to avoid this is by using the cross-validation. For example, in here, I use 5 cross-validation for each fold. It's gonna calculate the error, and the total error from this 5 fold will be the average for each of these fold. So that way, our training dataset is more robust, and it includes all type of labels. So here is the results of our KNN algorithm. So for example, when our KNN is 3, we got the accuracy as 1, and then our confusion matrix here is not that bad. It has like okay, 65 out of 65 we have 58 that is predicted correctly, and for KNN 10 is also just as good. But remember, this is using training and testing dataset using the same well, which is well A. So if we try another well as our testing dataset, for example, well B, and we see the results, we can say that here in our confusion matrix is not as good as before. So meaning that our model previously does not represent the reality. So what we need to do then, we try to go back again and reevaluate. And here, after we tried with the cross-validation 5-fold, then our confusion matrix actually show a lot better results. So it has 471 true positive. So in case of KNN, I would go with the cross-validation method first, and then only you refine the parameters. So this is the last slide. It's just going to be the summary of all the steps. Again, first, when we want to build a classifier model, is to clean the data. Make sure to take your time to select the best features, because not all the drilling parameters contribute weight to your estimator. You remember to replace the missing values using imputation, or maybe you have a better method for it. Again, and then double check again with scatter plot. That's the quickest, quick and dirty way to just get an overview of what is your independent variables. And not all, the more feature doesn't mean the more accurate your model is. In fact, I would say it's good to just start with as low as possible first. And then after that, after you chose the features, then you choose how do you want to split the data. So you can start just with normal 80-20% of your training testing data set. That can be a good start. And then from there you move on. It also depends on how your well data looks like. If you think there is not much of your tight zone, then it's good to do the cross-validation technique. But if you think there is enough of your tight zones that can be trained, then yeah, you can maybe just go with a much simpler approach. And then you choose the learning algorithm. Again, difference on your objective. In this case, I just want to know which zone is tight, which zone is the normal. So I only assign like two categories, 0 and 1, but if you want to use multi-class, it's also possible. But always start with the simples first. You can use, in this case, I try to use the SVM method, and also the KNN, but there are like still plenty of algorithm, and also um, you can experiment with different kernels. And in my case, it's completely linear data, but probably you encounter a more challenging well where it is non-linear, and then you can define your kernel parameters there. Again, after you choose the algorithm, and then only you start to refine the parameters, uh, adjust the hyperparameter, and testing a different data set, see the classification report, see the confusion matrix. So that is the last step, is to evaluate the model performance. You see the mean square error, and you see the correlation, and so on and so on, like repeat it one after another in order to get the robust data. So I think that's pretty much it.
Okay. Thank you so much, Bertha, for this insightful presentation. I really enjoyed it, to be honest, so much. Yeah,
Yeah.
I can see we have one comment. I think it's in a language I don't understand, but I can show it to you. It's someone asking for the slides, I think. Bert Kenapa, the slideshow or something. I don't know. What does it mean? Like, could you please send your slides or what?
Yeah,
It's from.
why can't I see the slideshow?
Okay, okay. Yeah, I
What
thought it
was
was
the-
someone asking for the slides of the presentation to be sent to them.
But was it like did I present it with a slideshow or?
Yeah, kind of, but it was not in full slideshow mode.
Oh
Yeah,
really?
but yeah, yeah, but it's fine. It's fine. Yeah,
I can't see it actually. Like okay, I'm really
yeah.
sorry because I'm like looking at the StreamYard.
Okay. Anyway, we have a question from Simon Larsen. He is asking, have you tried rock underscore AUC underscore score to see how well your classifier separates your classes?
No, I haven't actually. You mean no? I haven't. But is it like classes to separate the? I'm sorry. What was the question again?
I can show it to you now. The question says, have you tried rock underscore AUC underscore score to see how well your classifier separates your classes, like the
No, no, I
dataset
haven't
class?
tried, but I think I will try. Of course, if that is if that works. Simply.
Okay. And also, there is a question from me. Let's say, for example, if you don't have an example well with a tight spot, so how can that can be used as a training set? How can you still make a classifier model out of it?
So if you don't have, if you drill very safe and there is no indication of your tight spots, then yeah, unfortunately, you won't be able to build a good classification model. It is not possible. You at least need to have one data set that shows strong character of tight spot. You can probably simulate one, For example, you kind of set a threshold of your, for example, you have like very high ECD, 1.5, something like that, and uh, indicate it as a tight spot, but I don't think it would be very much reliable. So yeah, just at least get one well with tight spot in your exploration wells.
Oh, okay. Just for viewers, I forgot to mention at the beginning that my background is also in petroleum engineering. So for me, I'm
Yeah.
kind of curious. Yeah, I'm kind of curious to know the data set that you use to create the classifier model. Is it data that is collected pre-casing and cementing or post-casing and cementing?
It's open hole data. It's
Ah,
free.
okay.
Yes, yes, and also, sorry, what was that?
Yeah, like the data that you use to train the model, the data set from the wells, does it include the casing and
No,
cementation or just the borehole?
just the borehole. It's open hole. Uh,
Okay,
yes, and
okay,
and also it's when you use this. This is important that I didn't mention it in my presentation. When you run the when you choose the features to build this classification model, it's good to have the downhole measurements, not the surface. That makes a
okay,
big difference in your output, in your outcome. For example, I use the torque here. I use downhole torque, and but I know
hmm,
sometimes in some cases you don't have downhole torque, and you have to use the surface torque, which is from a top drive, and it won't give quite as good as your downhole torque actually. So
yes. For example, in the cases of on the balance drilling, I guess.
yeah,
Yeah, yeah. And also, there's something you mentioned during the presentation, which is kind of interesting to me also to know about. You mentioned when you don't have a non-linear well. By non-linear well, do you mean like a vertical well? And when you having data from a horizontal well, or what?
non-linear. I think what I mean by what I refer to non-linear is your data is, for example, like uh, this one. So
Okay, okay,
yes, yes. So it's more like your distribution of data, uh,
okay,
because then if you apply the SVM, if it is not non-linear, if then you have to apply a correction, you have to apply a polynomial kernel in order to be robust.
okay.
Yeah.
We also have one question from the audience, Arvind Kumar. It says, apart from viewing data, that is events, etc., are we also using other sources of data like logs or mod data, etc.? Yeah, it somehow kind of involves the process of casing and cementation.
Apart from drilling data, are we also using other sources of data like logs or mud data? So it's more like surface data then, right? It's not downhole. Um, you can, yeah, again, but I would suggest first to go with downhole, your downhole data, because you are trying to make prediction of your downhole condition. So your independent variables must also be downhole. So then it reflects the reality. It's not calculated one. So if you use smart logs, it is possible, yes, but I'm not really sure of how accurate it is. So you probably need to try several times. Like for example, in here you have to try to play around with your C data, how much margin you need to establish here, and you need to also plot the data if they are having like clustered or not. So yes, you can. I would say yes, you can, but double check it like with, yeah, more cautious if you don't use the downhole data.
Nice, Arvind. I guess your question has been answered. We still have 5 more minutes, so to our viewers, please keep your questions coming. You still have the chance to have your curiosity explained to you. Also, while we wait for questions from the audience, I will also like to inquire from you because you said you're still in the learning phase, and I want to know, like, have you? You're a professional operations engineer. Have you already used this method approach of yours to like solve business issues, like for clients, like to work on real wells, like on projects
Okay.
at your company? Yeah. I want to know whether you've already applied it or you're still just in the
So,
development phase.
well, that's a very good question. Um,
Yeah.
yes, it's okay.
You
Yeah,
know, nowadays the oil and gas industry is crazy about digitalization, and yeah,
yeah,
any
yeah.
opportunity to bring something innovative is usually
Right,
highly
right.
welcome. Yeah.
Yes. It's actually yeah, no, it's true. It's very relevant today. It's still like a black box mystery. So it's that's why if somebody can come up with like a robust model, a robust prediction, because it is number one priority for all well operators to know. They want to know where is the tide zone and how can I anticipate this. So if you could come up with a strong model, then it's going to be like a lot of it's invaluable input for them. And okay, regarding your questions, if I have applied it in business cases, so far, because it is not still like in the trying phase. No, I have not proposed this to client, but we used it internally. For example, me and my manager, what we normally previously we did is to with the drilling data we just try to plot and to kind of estimate. Also plotting, we use the matplotlib. But then after, the problem with just plotting is that you need to wait for the data first, right?
Yes.
You don't predict. You just like, okay, here I'm pretty sure 90% is tight spot, but you don't actually predict ahead of time. And then after we come up with this classifier model, we can actually predict it ahead of time, and it does come up quite accurate to when actually after they drill the well. So it's quite impressive actually. So maybe if any of you can wants any of you interested to propose this to client for business case, I think they would really welcome it. Uh,
Yeah, hopefully. Okay, it seems like we are coming to the end of this session. Uh, Thank you once again so much, Amalia, for taking your time. And it was really insightful. And we hope to see you next year also, hopefully, with more innovative
yeah,
approaches. It's really
I,
interesting.
yeah.
Yeah.
No,
Yeah. And
I'm waiting for you to also,
no
yeah,
worries, no worries.
do
Yeah.
something interesting for us.
Exactly. And to our audience and viewers, I am very grateful that you joined us to make this talk possible. And also, you can keep your questions in the comment section. They will be definitely answered too. Yeah. And also, thank you so much for taking your time. You can follow the rest of the talks that are planned on the events website. Thank you so much. Goodbye.
Goodbye. Thank you.
Bye.